Our project takes place in Playa Blanca, a remote fishing village of 250 residents located in the western coastal plains of Peru, with an arid climate and high fluctuations in temperature between day and night. Residents have access to a main pipeline system which contains water that is not suitable for drinking. Thus, with these constraints in mind, our team needed to design something that prevented widespread contamination while being financially realistic and providing at least 500 liters of drinking water a day with an ideal daily output of 1,000 liters. In our purification system, we will be redirecting water from Playa Blanca's main line for further disinfection and the removal of corrosive chemicals such as chlorine. This is so that residents can have access to drinking water without relying on energy-inefficient methods. At the end of the main line, water will be sterilized using a UV disinfection unit. This would ensure that both potable and non-potable water would be eradicated of pathogens, while saving costs by only using one large UV disinfection unit, which kills 90% of pathogens in the water. Next, this disinfected water will be transported in a separate extension plumbing line through a biomembrane filter made of activated carbon surrounded by cellulose acetate. This will remove macromolecules and harmful chemicals. After being filtered, the water will enter a family's home through a reverse osmosis chamber, featuring an internal structure similar to human kidneys. Using a 3-horsepower water pump to create high pressure, water would be filtered through another semi-permeable membrane. To prevent families from reducing electricity use on household appliances in exchange for drinking water, each family would receive the small-sized solar panel to power the motor. This would be connected to the current batteries used by WindAid, ideally a reusable 12.8-volt lithium-ion battery to store energy harvested during daylight. Moreover, in the event of a power outage, the reverse osmosis chamber will be outfitted with a hand pump, which would mechanically exert high pressure on incoming water to ensure that residents will be able to survive without an electric pump. Each family will be responsible for changing their own filters every 3 months and cleaning the reverse osmosis chamber at least once a year to remove macromolecules. However, with a UV disinfection unit in the main line and a double filter system, theoretically a family could survive much longer without changing filters before risking themselves to direct exposure to chlorine and potential pathogens. Despite the overall higher costs involved with distributing water to 50 personal filtration systems and using 2 biomembrane filters rather than just one, a higher filter count and having multiple water containers for each endpoint in the system will lower the chance of a widespread epidemic. If the system used only a single water tank container, a virus or bacteria sample could easily be spread by contamination of the main tank. Moreover, biofilters in the extension feed will combat accumulation within our input feed, thus increasing the overall yield in the system. We decided to take inspiration from the kidneys for a reverse osmosis chamber. Under high pressure, these organs filter blood to produce an aqueous waste product via small ducts called the ureters and a million nephrons which act as filters. Thus, we could mimic this by using a small pipe and high-pressure water pump to filter incoming water through activated or highly porous carbon, which would arrive in our version of the bladder, a water storage tank. With this 3-step system, the purification method ensures a sustainable future for Playa Blanca's residents to have access to drinking water for decades to come.